All right, we just have a few more to go through to wrap up these videos. Thank you so much for bearing with me in these crazy icy conditions and us moving to this asynchronous format just for this one day. 3 more problems here that I should be able to get through relatively quickly. We want to look at the ideas of intersections in the next 2 problems, then we'll spend some time doing some drawing stuff, right? So where does the line through these 2 points intersect the plane here? Now, whenever you think about intersections, you can always realize that there's going to be some sort of substitution that's going on. Substitution is really the process of having 2 equations, or multiple equations sometimes, and having that each of those equations represents a different type of geometrical object. It could be a plane, a line, a space curve, some sort of surface of different shapes. And when we're intersecting, we want to find what are common solutions to the different equations. So if I have one equation representing a line and another representing a plane, a solution to the equation is going to be a point on the line or a point on the plane. So if I'm looking for where they're intersecting, I'm looking for a point that is a solution to both. And so if I'm looking for something that's a solution to both, we find those via substitution. Now, depending on the situation that we're looking at, that substitution may look very different from one case to another, depending on the types of equations and the types of objects that we're looking at. Okay, I actually did a problem just like this in the last video when I was just trying to get a point A on that plane that moved with the plane. And I kind of just did this work offhand as I was trying to get the equation of that line to work properly. So, but now let me kind of show you what I was doing, what I was thinking, and how I went about that. So first, if I'm going to look at how a line through these 2 points intersects this plane, I need an equation of the line. I need some sort of mathematical object that allows me to manipulate it and plug things, somehow substitute one thing into the other. So my line, let's call it L of t, again is going to be a direction vector times t plus a initial point vector. So for us, our vector d is going to be 1, -1, 1. So the x goes from 2 to 3. So a change of 1. Y goes from -3 to -4. That's a change of -1. And the z goes from 1 to 2. That's a change of 1. So we have 1, -1, 1 for d. We're going to multiply that by t. And then we want to add an initial point. We can use either of these points. It does not matter for the equation of this line. Let's just go with that first point here. And if I write this out in parametric form, I get x of t equals t plus 2, y of t equals -t minus 3, and z of t equals t plus 1. And this is really what we want to do, because now I have expressions for x, y, and z that we can plug into the equation for the plane. Let's do that over here. For x, we're going to plug in t plus 2. Minus, for y, we plug in -t minus 3. And then for z, we plug in t plus 1. This equals 6 right here, right? So we'll go ahead and distribute 2t plus 4 plus t plus 3 plus 3t plus 3 equals 6. Combine some like terms. We've got 6t plus 10 equals 6. 6t equals -4, so t equals -2/3. Okay, so we've got a number here, t equals -2/3, but this is not the answer, because the question asks very explicitly, where does the line through these 2 points intersect the plane? And we've added in time in our parametric form. If we wanted a static form for a line in 3 space, we would need to use the symmetric equations, which we really tend to kind of avoid. Like, they aren't necessary. I can introduce time and then take it back out a little bit later, and these are just nice, simple ways of describing the line here. So this tells us when This is when the line intersects the plane. But it doesn't tell us where. So we just have one more substitution step to get that back. And that's just to plug this back in to our equation of the line. We could do that in the vector form, which is what I'm about to do. Or we could plug it into each of the components for the parametric form and get the exact same answer. So this is going to be 1, negative 1, 1 times negative 2/3 So if I then add the 2, negative 3, 1, you will get negative 2/3, positive 2/3, negative 2/3, and let's just get a common denominator here. And we get 4/3, negative 7/3, and 1/3. So this is where the line intersects. And that's our answer. That's it. Okay. So if we want to find how a line intersects a plane, we get the equation of the line. We take its x, y, and z components. We plug them in for x, y, and z respectively into the equation of the plane. We solve for t to find when the line intersects the plane, and then we go ahead and take the when, the t, and we plug it back into the line to get the point, the where it intersects the plane. So this point, 4/3, negative 7/3, and 1/3 is on this line. It falls between these 2 points. It actually falls before them, but it's collinear to those 2 points, and it also falls on that plane. So let's go ahead and move on and talk now about how do we intersect 2 planes. If I have 2 planes and I want to say where do they cross each other, they're going to cross in a line. So to get the equation of a line, I need a point on the line, and I need the direction of that line. Now, there's a couple of different strategies that'll get us through this, but I like going with a nice simple strategy. Like, we could do this with linear algebra really quickly. It's simply just solve the system of equations that we are given here, and you'll have a direction vector times t plus an additional vector, which is your starting point vector. So if you did this using an augmented matrix, you're going to be able to bust out an answer really quick. You just have to introduce a parameter partway through it. So I'm going to essentially do that, but I'm going to do it just without actually using any matrices. So I'm going to do a subtraction method here to get rid of the x's. So if I subtract these, I get 2y plus y is 3y. And then we get plus 2z equals 0. And we can then say 2z equals negative 3y, so z equals negative 3 halves y. And what I'll do now is I will let my independent variable here, the y, equal t. So z equals negative 3 halves t. And then we need to figure out how x relates. And we can do this by plugging these into either of the plane equations. So we can plug these, plug into either plane. we should get the same answer. So x plus 2 times t, y is t, plus 3 times negative 3 halves t for z equals 1. And we'll just solve for x in this. So this x plus 2, let's get a common denominator. My denominator is 2, so I'll say 4 over 2t minus 9 over 2t equals 1. X minus 5 halves t equals 1, so x equals 5 halves t plus 1. Now, if you go through and solve this in a different order, where say you eliminated y or z first at the beginning, then your answer can look very different, but it should still be equivalent. It should still give the same line. Let me go ahead and finish writing this out. So I've got my x, y, and z. I've got essentially my parametric form. If I want to write this in vector form, the direction vector is going to be 5 halves in the x direction, 1 in the y direction, negative 3 halves in the t direction, or in the z direction, I'm sorry. These are just the coefficients of t, plus a starting point. That's 1 on the x direction, 0 on the y, 0 on the z. So that's the constants in each of my parametric forms. But this is our final answer. So other answers may have a different starting point, but the direction vectors will always be multiples of this, right? So it may be 5, 2, negative 3 or something like that, right? But it will be an equivalent answer, and that can be shown pretty easily. So if you go through and you get the different answer than, say, the back of the book, or one of your classmates does it and has a slightly different answer, don't automatically assume that you're wrong, right? Go ahead and you can always plot these in GeoGebra and see whether or not you're getting the right answers. Let's actually do that right now. Let's look at the answers in both of these problems in GeoGebra and see how we can use the technology to confirm our answer. Okay, so let's start with problem number 5 here. And so the equation of the plane is 2x minus y plus 3z equals 6. The equation of the line was, t plus 2 for x, negative t minus 3 for y, and t plus 1 for z. T is our variable, negative 10 to 10 usually should do just fine here. Let's plot the 2 points given, 2, negative 3, 1, and 3, negative 4, 2. So these are the 2 points that we were given that we said we know are on the line, which yes, they are, so that's good. That means we got the correct equation of the line. And we're looking for where that line intersects that plane. So we can see it's like right here. Let's go ahead and plot that point that we got as our answer, 4/3, negative 7/3, and 1/3. And we see that it does in fact fall at that intersection. So that's great. That's just us being able to use the technology to confirm our answer, to know that it did what we wanted it to do. So let's go ahead. Let's go ahead and just delete these. And start over. X plus 2y plus 3z. So now looking at number 6, x plus 2y plus 3z equals 1. And the second equation was, oh, I've got it right here, x minus y plus z equals 1. And then the line of intersection that I found, we can see that intersecting line right here. That makes it real nice and obvious, right? at that location. And so let's do curve, and the x component we had as 5/2 t plus 1. The y component is just t. The z component is -3/2t. And we'll say t is our input variable. Go from -10 to 10. And boom, that falls right on that intersection as we were expecting it to. Yes? So that's how you can confirm your work here. All right, we've got one more problem to do, and it has to do with graphing planes. Let's just go ahead and graph that plane for number 7 before I jump in to do it by hand. Delete. And we've got -2x plus 3y plus z equals 6. So if I took this, and I'm going to zoom in a way that we like to draw things. So here, I like to draw things like this, right? With my x down to the right, y into the board, and z up. I'm going to hold the shift key down and latch onto that z axis and stretch until I can get that plane intersecting that the z axis pretty clearly here. So pull it up a little bit farther. So let's find a few points. If I have x and y both 0, then I just have z is 6. So at this point is where the plane intersects the z axis. If I had x is 0 and z is 0, then y would equal 2. Right, so if I plugged in 0 for x and 0 for z, then I'll have 3y equals 6. I divide that 3 off, I get a 2 for the y, and that gives us this point right here. And finally, if I took and I plugged in 0 for y and z, I'd have -2x equals 6, so x would be -3. Y and z are both 0, and that gives us this intersection of the plane with the x-axis. Yeah. Let's pull this back over to here. And actually I can see by graphing it in 3 dimensions, it's going to be a lot easier to draw this picture from this angle. So on the paper, I'm going to take this advice from the computer and say, okay, I want to draw x direction this way, y direction this way, z direction up, as we do in this class. Now the traces are the lines between these points. So if I look back, if I look at my equation and I just set, if I just take z equal to 0, we get -2x plus 3y equals 6. Now this is the equation of a plane in 3 dimensions, but let's take this if we can. But what I really care about is how it's just connecting the points B and C in the xy plane, right? So this, rather than thinking of this as a plane on the paper as I'm drawing things, I'm just going to draw this connecting line between these 2 points. So let's actually, the whole point of this is to be able to do this on paper. So let's just kind of use this as a starting place, and I'll show kind of how I'm going to use these equations on the paper here. So let's close this down and go back to the paper. Again, if you have isometric paper, I do very much recommend that. So I'm going to use what I saw on the screen to inform me that this is a nice orientation for everything. If x is 0, we get if x is 0 and y is 0, we get z equals 6. So that's the point 0, 0, 6. If x is 0 and z is 0, then we get 3y equals 6 or y equals 2. So that gives us the point 0, 2, 0. And if y is 0 and z is 0, then negative 2x equals 6, so x equals negative 3, and we have the point negative 3, 0, 0. And so that's about here. Now the line, if z equals 0, the line between 0, 2, 0 and negative 3, 0, 0 is negative 2x plus 3y equals 6 in the xy plane. So we could solve for y here. Y equals 2/3 x plus 2. So if x is 0, y is 2. And then if x is negative 3, we'd get y is 0. So that gives us these 2 points right here. If x is 0, then I get 3y plus z equals 6. If I solve for z here, I get z equals negative 3y plus 6. So if y was 0, then z would be 6. If y is 2, then z would be 0, and this connects these 2 points right here. Finally, if y equals 0, we'd have negative 2x plus z equals 6. I'm going to solve for z again. Z equals 2x plus 6. And if x is 0, z is 6. If x is negative 3, z is 0. And this is going to connect these 2 points. And so we get that our plane is going to go through those 3 points right there. And that's kind of the key to drawing this. So I might take and redraw this and rotate things a bit more. The x-axis kind of this way and the y-axis over here. And I'm going to draw the lines through these points, which are the traces. The traces are when you just set one of the variables to a constant and then get the lines out of that. And we could try and draw some more lines here, but we're going to quickly see that things get cluttered. So if I take that line through these 2 points, and just copy it and make it parallel, but through this point, and we can kind of do that with all of these. I could take this line here and copy it. Try and draw a parallel to it over here. And then this line and try and draw it over here. And we quickly see things get cluttered and it's tough to see what's going on. So I almost don't recommend adding anything and just having these be the only lines, and we recognize, like, you could do something that might help of just taking a couple of these and drawing them a little bit more, like a couple more copies of them, but it just gets so cluttered and it gets hard to see. So the main thing I want to see is this triangle with the lines extended beyond them, okay, that you're understanding how to get those 3 points, those 3 lines, and draw them. So show the math for it and draw the picture, and this is what the expectation is something to about this quality, okay? All right, that's it. That's the last of what I've got to show you for this. Thank you so much again for bearing with us in this tough time. shoot me an email with any questions or concerns. I will be sure to get back to you as soon as I can. All right. Thanks much. Stay safe out there. Bye-bye.